The flour in the bowl barely burns, but throw the same powder into the air and one spark can turn it into a fireball. That statement sounds like it belongs in a chemistry lecture full of dramatic demonstrations. But it describes a genuine physical phenomenon that has shaped how engineers design buildings, how regulators write safety codes, and how workers understand the spaces they spend their days in. The question worth keeping in front of us is simple. What exactly changes when a solid material becomes a cloud? The answer reaches into the physics of surface area, the chemistry of oxidation, and the brutal engineering reality of pressure. Start with the bowl. You can hold a handful of flour, hold a lit match above it, and watch almost nothing happen. The flour chars a little at the surface. Maybe a small flame travels slowly across the pile. Nothing dramatic occurs. This is flour behaving the way most people intuitively expect a food ingredient to behave. It is not obviously dangerous.
It does not feel like fuel. And in that familiar static form, it largely is not. Now imagine that same quantity of flour thrown into the air inside a room. The individual particles, each one a tiny fragment of starch and protein, separate from one another and float suspended in the atmosphere. Each particle is now surrounded on all sides by oxygen. Every surface of every grain is exposed. And this is where the physics changes in a way that is genuinely startling. The key concept is surface area, and it matters more than almost anything else when we talk about how quickly a material can react with oxygen. Think of a log burning in a fireplace. The flame consumes the outside of the wood, and combustion proceeds at a pace governed by how much surface is available to the heat and oxygen. Now imagine taking that same log and reducing it to sawdust, and then spreading that sawdust through the air.
You have not changed the chemical energy locked inside the wood. You have not added anything, but you have multiplied the exposed surface area by an enormous factor. The reaction now has access to the entire mass of material at once, rather than working its way slowly inward from one face. This is the physical heart of the phenomenon.
Combustion is a chemical reaction between fuel and oxygen, and like all chemical reactions, its rate depends on how thoroughly the reactants can contact each other. When fuel is a solid block, contact is limited to the outer surface. When fuel is a fine powder suspended in air, contact is effectively total. The reaction can proceed through the entire mass of material almost simultaneously. For flour, this matters enormously. Flour is composed largely of carbohydrates, and carbohydrates are carbon-based molecules that release energy when they oxidize. In the bowl, the oxidation is slow and surface-limited. In a cloud, if ignition occurs, the oxidation can propagate through the suspended material as a flame front moving through a medium that is, in effect, a distributed fuel source. The flame travels from particle to particle with almost nothing to slow it down. Now place yourself somewhere more concrete. A worker enters a flour mill early in the morning. The building has been operating for years. Flour dust has settled on the beams overhead, along the ledges of machinery, in the corners where the brooms never quite reach. The accumulated dust is unremarkable. Everyone who works there has seen it every day. It is background. It is ordinary. The worker is not thinking about chemistry. They are thinking about the morning's workload, the machinery they need to start, the small complaints of a routine job. What they may not fully register is that the building around them has been slowly transformed by its own ordinary operation into something with a different set of properties. The dust on every horizontal surface is stored fuel. It is not dangerous in the way a barrel of solvent is dangerous, obvious and labeled and cordoned off. It is dangerous in a way that requires a specific set of conditions to become apparent, and those conditions can arrive without warning. The fear embedded in that moment is not theatrical.
It is the fear that everyday neglect, the ordinary accumulation of an ordinary substance, can quietly convert a familiar workplace into a trap. Safety researchers and regulators have developed a framework for understanding when and why combustible dust becomes a genuine hazard. You may be familiar with the fire triangle, The model that says fire requires heat, fuel, and oxygen simultaneously. Combustible dust explosions require those three. But the framework expands to what is described as a pentagon, adding two more necessary conditions: dispersion and confinement. Dispersion is what we have already discussed. The material must be suspended in air, mixed with oxygen, at a concentration that supports combustion. Too little dust and the flame cannot sustain itself. Too much, and there may not be enough oxygen to support propagation. Within a certain range, however, the mixture becomes what engineers call explosible. Confinement is the second addition, and it is what turns a fast fire into something that behaves more like an explosion. When combustion proceeds rapidly inside an enclosed space, the heat of the reaction causes the surrounding gas to expand. In open air, that expanding gas simply pushes outward and disperses. Inside a room, a duct, a silo, or any enclosed structure, the expanding gas has nowhere to go. Pressure builds faster than the structure can relieve it. If the pressure rise outpaces the structural limits of the enclosure, the building fails. The failure is violent and sudden, and it produces the characteristic destructive effect associated with an explosion, even though the underlying process began as ordinary combustion. OSHA includes flour among the materials that can form combustible dust hazards, alongside sugar, wood dust, coal dust, and many other common industrial substances. The list is deliberately broad because the underlying physics applies across a wide range of organic and some inorganic materials. The specific energy content of each material differs, and so does the exact concentration range that supports combustion, but the general mechanism is consistent. What makes a material a combustible dust hazard is not some exotic chemical property. It is the combination of being finely divided, being capable of oxidation, and being present in an environment where the other pentagon conditions can be met.
The progression of a dust explosion in a real industrial space often follows a two-stage pattern that makes the hazard significantly worse than a single event would be. A primary explosion occurs somewhere in the facility, perhaps triggered by an equipment spark, an overheated bearing, or any one of dozens of routine ignition sources present in industrial environments. That primary event, even if it is relatively small, creates a pressure wave that travels through the building. The pressure wave disturbs the settled dust on every beam, every ledge, every surface where it has accumulated over days or weeks or months. That dust becomes suspended, it disperses. And now the secondary explosion has access to a fuel source that may be orders of magnitude larger than what fed the primary event. The secondary explosion is where the catastrophic structural damage typically occurs. This sequence, primary dispersion then secondary ignition, is why facilities that handle flour, sugar, grain, and similar materials are required to maintain rigorous housekeeping standards that might seem excessive to someone unfamiliar with the physics. The settled dust is not merely unsightly, it is potential fuel for the second stage of an event that might otherwise have been manageable. Keeping it off surfaces is not a matter of aesthetics. It is a matter of removing one of the 5 sides of the pentagon before the others have a chance to align. Wood dust follows the same logic, so does powdered sugar, so does fine coal dust. The specific substances differ, but the underlying mechanism does not. The material that seems inert in bulk reveals a completely different set of properties when reduced to particles small enough to stay suspended in air. This is not a marginal effect. The difference between the bulk material and the dispersed cloud is not a modest increase in flammability. It is a qualitative shift in how the material interacts with oxygen and with the energy of combustion. That shift is what makes combustible dust one of the more counterintuitive hazards in industrial settings. People who work with flour every day and have never seen it behave dangerously have good experiential reasons to underestimate it. The danger is not in the material as they routinely encounter it. The danger is in the geometry, in the specific arrangement of finely divided fuel, oxygen, ignition source, and enclosure that transforms a familiar ingredient into the mechanism of a rapid pressure event. So back to the opening question. What changes when a solid material becomes a cloud? The answer is surface area, and surface area changes everything. The chemical energy in the material was always there. The capacity to react with oxygen was always there. What changes is the rate at which that reaction can proceed. And rate is the difference between a slow char and a flame front that travels faster than any structural response can contain. The flour in the bowl is the same substance as the flour in the cloud. The physics are the same. The chemistry is the same. What differs is the geometry of the encounter between fuel and oxygen. And in that difference lives the entire explanation for why engineers treat dispersed combustible materials with the same seriousness they bring to flammable liquids and gases. The next time you find yourself wondering why a building might seem over-engineered, why ventilation systems in industrial facilities are built to specifications that seem far beyond what a food ingredient would seem to require, or why housekeeping standards in a grain elevator are written into law rather than left to discretion, the answer traces back to this same principle: geometry, surface area. The way that matter behaves differently, depending not just on what it is, but on what shape it takes in the world. And that question, how shape and arrangement can transform the danger profile of an ordinary substance, reaches well beyond flour. The same logic describes how metal powders become hazardous in manufacturing, how coal dust has shaped the history of mining safety, and how the study of dispersed phase combustion continues to inform the design of everything from industrial facilities to propulsion systems. That is a story worth following.